I'm Jennifer Dye, a librarian at Detroit Public Library. DPL has offered astronomy programs for the last several years. When things fell apart in spring 2020, programs were put on hiatus. We finally launched astronomy programs on Zoom earlier this year. We feel that these have worked well. Over the summer, Megan McCullen, director of the Wayne State University Planetarium, and I applied to an initiative sponsored by the NASA Goddard Space Flight Center for programming around the launch of the James Webb Space Telescope, which was scheduled for December 18th. It's now been postponed until at least December 22nd. In October, Dr. Mark Christensen presented the first program about the technology and testing of the telescope. Dr. Edward Cackett will talk tonight about the science goals of the telescope. I'd like to ask Megan McCullen to speak briefly.
Thank you, Jennifer. On behalf of the Wayne State Planetarium and our Department of Physics and Astronomy, I just want to say thank you to everyone for joining us, and thank you to Dr. Cackett for agreeing to give this presentation. I get to hear Dr. Cackett talk about his research a lot, but it's nice to be able to share it with the public whenever we get a chance. And so this was a really great opportunity to do that. He's been doing all sorts of work with an array of telescopes, and now he's going to add another one to his list. So we're really thrilled to be able to share this with everybody. And thank you to Jennifer for doing a lot of the legwork on this. I did some of the upfront, but a lot of this coordinating the actual events has been all on her. So thank you for doing that. And we'll be posting links to upcoming events in the chat as we go. We'll post them at the beginning and then again at the end to let you know about other upcoming planetarium events and library events and events we're coordinating together. Thanks.
Thank you. Now, Ed Cackett grew up in the suburbs of Manchester, England, and studied physics at the University of Durham before pursuing his PhD in astrophysics at the University of St. Andrews in Scotland. After that, he spent 4 years as a postdoctoral researcher at the University of Michigan, where he was a NASA Chandra Fellow, and 1.5 years as a research fellow at the Institute of Astronomy, University of Cambridge. In 2012, he made the permanent move back to Southeast Michigan to become a faculty member at Wayne State University, where he is currently an associate professor. He has published over 180 articles in peer-reviewed journals. He is an expert in X-ray observations of black holes and neutron stars. We're fortunate to get his knowledge this evening. I haven't had Megan's opportunities to hear him. Please welcome Dr. Ed Cackett.
Thank you both. It's great to be here tonight to tell you about the exciting things that the James Webb Space Telescope will be doing after it launches, fingers crossed, in a few weeks' time. So I called the talk Searching for the First Stars because really that's one of the main goals that's driving building the James Webb Space Telescope. But there's a wide range of science topics that the Webb telescope will address. And so I'm going to touch on each of these and give you a sort of a tour through the sorts of things that Webb will do once it's in space. So last month, many of you, I'm sure, listened to the great talk by Mark Christensen telling you all about the technology behind the James Webb Space Telescope. Today, I'll just briefly tell you a bit about JWST for those of you who have not heard about it before, and then describe why we need it. And then I'll go on to talk about the main science themes that have driven the development of the James Webb Space Telescope. And that's studying the early universe, so looking at the very first stars and galaxies, understanding how those galaxies change over time to become the galaxies that we see in the universe, in our local universe today. And then how in those galaxies, how stars form and how planets form around those stars, and then how we can try and find planets where that are potentially habitable by searching for signatures in their atmospheres using the Webb telescope. So the precursor to Webb that's still flying is, of course, the Hubble Space Telescope, launched over 30 years ago in 1990. And it has, of course, done some absolutely amazing science in the last 30 years. So it was the first major UV optical space telescope. It has a diameter of 2 meters, and it's been orbiting the Earth at an altitude of something like 560 kilometers for the last 30 years. It was launched on the space shuttle, and so it was actually designed to be serviceable by astronauts. And in fact, there have been a number of service missions over its 30-year lifetime to fix things and improve instruments and keep it going strong. And it has done some fantastic work. So it has created images like the one here on the bottom, this is the Hubble Ultra Deep Field, which looks back to some of the earliest galaxies in the universe. And then fantastic pictures like this on the right-hand side. This is famously known as the Pillars of Creation, which are these towering molecular clouds that are cold, dense gas where stars are forming. So Hubble has done some fantastic things, but it's a platform for us to build on. And the science that we've discovered and been able to do with Hubble is really a launching pad for what we can do with the James Webb Space Telescope. So how has the James Webb Space Telescope, how is it going to improve on Hubble? So as I said, Hubble is a telescope with a 2-meter diameter. So just to give you the sort of size comparison you can see in this figure here. Whereas James Webb Space Telescope is going to have a 6.5-meter diameter mirror made of 18 segments of gold-coated beryllium. Each of these segments is about 1.3 meters across. So it's going to have about 10 times the collecting area of the Hubble Space Telescope. So that makes it significantly more sensitive. It was first discussed before Hubble had even launched in 1999. And the first full sort of concept designs came about in 1996. And at that point, it was hoped that it would be able to be launched in 2007. Well, 2007 came and went, and there have been many delays since then. And in fact, it survived even the threat of being cancelled in 2011. But we are now just a few weeks away from the launch of this next great space telescope. And what makes James Webb different from Hubble, aside from the fact that it's much bigger, is that it is more sensitive to and designed specifically to look in the infrared part of the electromagnetic spectrum. I'll tell you a bit about that in a few minutes. When we look at pictures of Hubble, you don't ever see the mirrors directly. It's actually covered by foil, right, that sort of blocks it, the light from the Earth and from the sun getting onto the mirror. The way that they've designed this with the James Webb Space Telescope is to put these huge tennis court-sized sun shields to protect the telescope from the sun. And the way that it works is that the sun shields will always face the sun. On the hot side of them, there'll be something like 185 degrees Fahrenheit, but they will protect the telescope and its sensitive instruments and keep them down at minus 388 degrees Fahrenheit and keep them working in optimal temperatures so that they can get the most sensitive data possible. Of course, something that is, well, so this is an image that was taken in the labs at the Goddard Space Flight Center, showing the testing of these sun shields. These are fully extended. The mirror, how you can see, is folded up. And this is because something that's a tennis court sized satellite does not fit inside a rocket. So to be able to get this up into space, this has to be folded up very carefully so that it can fit inside the casing of a rocket and be launched into space. Just to give you an idea of size scale, here's a full-scale model of Webb telescope on the grounds of the Goddard Space Flight Center, compared to the large team of folks who've been working on it there. So this is its current status. It is in its folded up position, all tucked up nicely, and it's currently sitting inside the nose cone of the rocket. So it is in French Guiana on the northern part of South America, which is where the European Space Agency has its launch site. It's going to be launched on an Ariane 5 rocket, which is what is needed to be able to get it to where it's going to go to. And it's currently scheduled for a launch on December the 22nd. It was initially supposed to launch on December 18th. And then NASA made this statement where saying a sudden unplanned release of a clamp band, which secures Webb to the launch vehicle adapter, caused a vibration throughout the observatory, which to me sounds like they dropped it. They may have only dropped it a little bit, but something caused a vibration through the observatory, which worried them. And they spent a couple of days doing some extra tests, found that it was all okay. And so now it's scheduled for a 7:20 a.m. Eastern launch date on December the 22nd. So fingers crossed, that's when it will go up into space. And it's actually not going to be in orbit around the Earth. So Hubble, as I said, is at an altitude around about 570 kilometers. It orbits around the Earth. Where we're placing Webb is 1.5 million kilometers away from the Earth, further past the moon, at a special gravitational spot called L2. This is where the gravity of the Earth and the Sun essentially balances and makes a stable place for the telescope to be. So Webb will actually be orbiting around the Sun rather than orbiting around the Earth. And this is what its orbit will look like. It's going to have an orbital period of 1 year, just like the Earth. And then it actually does a little epicycle in its orbit so that it can always view the sky and doesn't get, always the solar panels can always see the sun, and it doesn't fall into the shadow of the Earth and the sun. And of course, once it's launched, they need to unfold it. And so here's a little animation showing you how they're going to do that. This is what it looks like when it gets out of the rocket. 30 minutes after launch, they're going to get the solar panels up and going. In 2 hours, they're going to get the antenna going so they can communicate with the ground. It'll take about 30 days to get to L2. On the third day, they're going to start to unfold the sun shield. And they're going to take their time to make sure they can test everything. And then they're going to start to unfold sun shield. And then pop out all the different layers so that it can work properly. After 10 days after launch, they start getting the mirror unit working. So this is the secondary mirror. And then they will fold out to the rest of the primary mirror. To get the telescope full working order. And then they'll do a final burn on day 29 to get it right into orbit where it needs to be. So I'm just going to zoom back just a little bit to give a picture of the telescope here. Yeah, so here you can see the sunshade, which blocks the sun. The light from the stars and galaxies will hit the primary mirror, be reflected to the secondary mirror, and then go through this gap here in the center to the detectors that are sitting behind the mirror. Okay, so it's designed to be sensitive to infrared light. So what's infrared light? So all light is part of the electromagnetic spectrum. So all from radio waves all the way through to X-rays and gamma rays are the same thing. They're photons of light. They just have different wavelengths. So visible light that we see with our eyes, the rainbow spectrum colors is here, whereas infrared has slightly longer wavelengths than visible light. So why would we want to look at the universe in infrared light rather than visible light? Well, the first reason is because we want to be able to peer back in time as far as possible. So why does that mean that we need to look in infrared light? Well, that's because for about the last 100 years, we've known that the universe is expanding. And the expansion of the universe has an effect called cosmological redshift that means that objects that are far away from us their light gets shifted to the red part of the spectrum. So essentially what happens is when we're looking at an object that's far away, we are seeing the light as it was several million years ago or billions of years ago. And that light was maybe emitted in the ultraviolet part of the spectrum. So it had a very short wavelength. But as that light has traveled on our way to us, the universe has expanded, space has expanded. And that stretches out the wavelength of light. So that by the time it reaches us, that light is now longer, significantly longer wavelength and has been stretched from being ultraviolet light all the way to being infrared light. So the further back we look, the further away an object is, the faster it's traveling away from us because of the expansion of the universe, and the more its light gets shifted redward. And so this means that by building a telescope that's sensitive to infrared light, we can then best look at distant objects in the early universe. So infrared light means we can peer back into the past and look back to when the first stars were formed. So with Hubble, we've been able to get the view, the sort of really at the limit of maybe when some of the first galaxies were formed. With Webb, we should get significantly further back to look at those first stars. Why else might we want to build an infrared telescope? Well, another reason is to peer through dust. So if anyone's ever seen the Milky Way, here's an image of the Milky Way in the sky. Every single one of these white dots is a star. This black cloudy stuff in the way is not that there's no stars there, it's that there's lots of gas and dust in the Milky Way that's blocking our view. by dust here, we're meaning small particles, silica particles, that readily absorb optical light. So it blocks our view of the stars behind. So how can we look through that dust? Well, we can use infrared light. To give you an example, here is a man here with a trash bag over his hand. And when we look in optical light, we can only see the trash bag. Once we look in infrared light, we can see his thermal radiation, his heat. And that actually allows us to see through that trash bag. And now we can see his arm and his hand, right? So infrared light lets us look through obscuring material. So here's an example of that. This was taken by the Hubble Space Telescope. This is known as the Carina Nebula. So in the top here is an image in optical light. And you can see these big clouds of dust. This is where stars are forming. And once you go into the near infrared part of the spectrum, you start to be able to see through that dust clouds and actually be able to see the stars that are hidden. And you can see a young star here that's actually got some jets of gas that it's spitting out. Right, so going into the infrared lets us peer through dust and see what's going on. Okay, so that's a sort of a quick tour of what the Webb Space Telescope is and why it's been built and why it's an infrared telescope. Now I'm going to go through each of these 4 science areas and themes and talk a little bit about why these are super interesting. So the first one is this early universe theme. And so the key question is asking, what are the first galaxies? What are the first stars? And so to do that, we have to look at galaxies that are far away from us, because the more distant a galaxy is, the longer it is taken for the light to reach us. So we are effectively viewing them as they were in the past. So just to give an example, if we think about looking at stars in our own galaxy, the Milky Way, those stars are something like 20 light years away, which means, 2,000 light years away, which means it's taken about 2,000 years for the light from that star to reach us here on Earth. So we are looking at the stars in our Milky Way as they were when the Romans ruled Europe. When we look further away, say, for instance, at the nearest galaxy cluster, like the Virgo cluster, that's 65 million light years away. So that's the light that we're seeing from the galaxies in the Virgo cluster now left those galaxies when the dinosaurs were on the Earth. Going further away still, if we look at a young galaxy that's maybe 4 billion light years away, we are seeing light that left that galaxy when the Earth had only just been born and was extremely young. So as we look further and further away, we are looking further and further back into the past, into the earlier and earlier universe. So Hubble did some fantastic work in this sort of area and has taken the most sensitive image that we have of the universe today. It started as the Hubble Deep Field, and over the years, it's become deeper and deeper, and now is known as the Hubble Extreme Deep Field. In total, it took more than 50 days of time staring at the same part of the sky, with the data taken sporadically over a 10-year period. And every single one of the smudges you see in this guy on this image are distant galaxies. And the most distant galaxies in this image are, as you see them, only 450 million years after the Big Bang. Just for comparison, the universe is something like 13.7 billion years old. So 450 million years after the Big Bang is really very early on in the universe. But with Webb, we hope to do much better. So why do we want to look back deep into the early universe? Well, when we look at local galaxies, they have beautiful spiral structure or elliptical structures. But when we look in the Hubble Ultra Deep Field, the galaxies look quite different. Earlier in the universe was much more chaotic. The galaxies didn't have the same beautiful structures we see today. They were a lot closer together. There were lots of collisions going on between galaxies. And so to be able to understand how the galaxies we see today came about, we need to start to look at and look back in time to look at these early galaxies. So how far back do we need to go? Well, the universe formed in the Big Bang, an explosion that started off the universe with a huge expansion. After about 400,000 years, the universe cooled enough to start to be able to form atoms and nuclei. At that time, these nuclei are extremely good at absorbing light. And so this gets known as the Dark Ages. So it's a period where the universe was extremely dark. However, after about 400 million years, the universe had gotten cold enough that stars could start to collapse out of gas clouds and ignite, and we get the first stars. Those first stars start to ionize the universe, and light can travel freely through the universe again. This period is known as reionization. And so what we want to do by looking back as far as possible is to try and see the signatures of the first stars reionizing the universe and ending what's known as the Dark Ages. So the sort of history of how things have gone, in 1990, before a Hubble Space Telescope, we could only get back to something like 6 billion years ago, or 6 billion years, after the beginning of the universe. As Hubble has gone deeper and deeper and deeper, we've gotten to something like 480 million years after the Big Bang. And with James Webb, we're expecting to get something like 200 million years after the Big Bang and get back to that really early age of the universe. And this is just an example, a simulated example of what things might look like with James Webb compared to Hubble. So here is one of the galaxies in the Hubble Ultra Deep Field blown up. Looks kind of smudgy and blurry. With JWST, we should start to be able to see star-forming regions going on, and you can see the many extra additional faint small galaxies that we should be able to pick out. And looking at those galaxies addresses our next question. How have galaxies changed over time? So we form these first stars, and these first stars then go on to form the first galaxies. But the galaxies that we see in the Hubble Ultra Deep Field do not look like the galaxies that we see in our local universe. So here's just a couple of examples of galaxies that are not so distant from us. On the left here is a beautiful spiral galaxy known as NGC 1566, where you can see the wonderful spiral arms, and you can see these dust lanes and regions where stars are forming. So there are many, many spiral galaxies in our local universe. Then there are also lots of elliptical galaxies. Elliptical galaxies are these galaxies that are sort of spheroidal in shape. They don't have any of these spiral arm sort of structures. And we often find these at the very centers of galaxy clusters. So we want to understand, how did we get from the very early galaxies to the galaxies that we see today? And we can try and understand this by looking at what goes on in these distant galaxies. Again, here is an image of the Hubble Ultra Deep Field with just some galaxies picked out. And you can see that their shapes are nothing like the beautiful spiral galaxies, elliptical galaxies that I just showed you. They have lots of clumps, lots of irregular structure. And so they clearly were not like the galaxies that we see at the current time. So we want to understand why this is the case. Now, it's thought that a big part of this is the merging of galaxies. So in our relatively local universe, we actually see this taking place quite frequently. Here's a famous example. This is known as the Whirlpool Galaxy, and it has a little companion here, which is in the process of merging with it. Our own Milky Way is actually on a collision course with the nearby massive galaxy Andromeda. And in the future, these two will collide and merge together as well. And Hubble has seen an array of galaxy mergers taking place. So here's just an example of all the different sort of stages of galaxies merging together. And we think that this is a really important step for forming the shapes of galaxies and the types of galaxies that we see today. And this was prevalent early in the universe when galaxies were much, much closer together. And typically the first galaxies were a lot smaller. And they've grown by merging together to become bigger and bigger galaxies. So astronomers have tried to understand this through simulations. So we can use supercomputer simulations and to sort of understand how structure in the universe may progress. So what you're seeing here is galaxies being pulled together by gravity and in the process of merging together in the early universe. So for many, many smaller galaxies in the early universe, irregular shaped things, you start to form bigger, more regular shaped galaxies that we see today. Here's another little example of that, how you can get spiral structure caused by the merging of different galaxies. Again, many smaller galaxies merging together to make one much larger galaxy. And so to understand exactly how this process works to inform the supercomputer simulations, we need to have real data about what the structure of galaxies is in the early universe, how many there are, what the star formation rate is in those galaxies, and then piece together a picture of how they get from what they were then to how they are now. One of the things I'm particularly interested in is supermassive black holes at the centers of galaxies. And it seems that supermassive black holes that are millions to billions of times the mass of the sun, that sit at the centers of every major galaxy in the universe, are tightly linked with the host galaxy that they sit within. And so to understand how they influence each other, we again want to look back as far as possible to see how the black hole and the galaxy co-evolve and grow together. So there are a number of interesting questions about how galaxies form and how they change over time that James Webb Space Telescope is ideally suited to look at. Okay, so then bringing it a little closer to home, we can think about using the James Webb Space Telescope to understand how stars form, how planetary systems form, and then even searching for signatures of life around other planets. And so this next theme is understanding the life cycle of stars. And why James Webb Space Telescope is so good for doing this is because it's sensitive in the infrared part of the spectrum. And because it can see through dust to actually get a clear view of the stars that are forming. So stars form out of these giant molecular clouds, like the pillars of creation that I showed you before. And those clouds are turbulent, and they have areas that are at higher density than others. And those higher density areas, the gravity of them pulls them together. They collapse down and they heat up. Eventually they get hot enough to start nuclear fusion and become a star. And as they collapse down, because this material is turbulent and rotating around, they tend to form a disk of gas around them, gas and dust around them, and they can send jets spitting out from either side of this protostar. And then around the protostar, we have this disk, which is known as a protoplanetary disk. This is the material out of which planets form. Eventually, you end up with something that's like our solar system. So with the Webb telescope, we want to understand each of these steps, how we get from molecular clouds to ending up having solar systems, and solar systems like our own and others. Here is an example of what Hubble's been able to do. This is a protostar named as HH30. Here you can see that in green, a jet of gas that's been spat away, and then the disk of the protoplanetary disk that's surrounding this protostar. So again, just to reiterate, we have to go to the infrared if we want to be able to see into these clouds of dust. So again, this is a beautiful optical image of the Hubble by the Hubble Space Telescope of the pillars of creation. But it's only by going to the near infrared that you start to see the stars that are formed within. So this is a Hubble Space Telescope near infrared image of this. So let me just show you that again. Here is what we see in the optical. We cannot see through these clouds, and we see very, very few stars. As we go through to the near infrared, we start to be able to see through. We can see the young stars that have been formed, and then we can actually start to learn about what the conditions are in these clouds that allow these stars to form, and have a better idea of how stars end up forming. Here's another great example of that. On the left is an image from the Canada-France-Hawaii telescope of the famous Horsehead Nebula in optical light. Again, this is a molecular cloud where stars are formed. And here is a near-infrared Hubble Space Telescope image of the same region. Again, once you go to the infrared, you can start to see the regions where these new stars are actually formed. And again, in the same way that supercomputer simulations allow us to get a good idea of what the physical conditions are that form the first galaxies, we can also use supercomputer simulations to try and better understand how these big clouds collapse down to form stars. So here you can see in this turbulent cloud, this region here is where some stars are forming and collapsing down. And as you zoom in further, you can actually start to see the stars, the protostars forming, and even see protoplanets forming around these protostars. So Webb observations of giant molecular clouds in the infrared give us the data to better understand the conditions needed to form stars, and therefore the conditions needed to form planets and solar systems. And we can do things like this. This is a beautiful image taken by the ALMA telescope, which is a sub-millimeter telescope in the Atacama Desert in Chile. This is a young star named HL Tau, and this is the protoplanetary disk. So the sort of glowing orangey yellow stuff is the gas, And you can see in black, there are multiple gaps and rings in this protoplanetary disk that are thought to be caused by emerging planets sweeping their orbits clear of dust and gas. So by looking at young systems like this, with Webb, we can start to understand how planetary systems form. And again, those observations with Webb help inform computer simulations and give us an idea of what the physics is of why and how stars form and how planets form out of the same disk of gas and dust. This is just showing you the formation of several protoplanets in the disk around a young star. So with Webb, we can start to learn about the formation of stars, the formation of planets around those stars. And then you get to ask the question, well, out of these planets that form around these stars, will we be able to determine which of these planets could potentially have life on them? And this is the final theme of the major science themes for Webb, is to look at other worlds. So in the last 25 years, astronomers have discovered something like more than 4,000 extrasolar planets around other stars. And so you want to ask the question, what are planets around these other stars like? Are any of these solar systems look like our own solar system? Are the conditions on any of these planets right to be able to harbor life and for life to be able to start and exist? From what we've learned so far over the last 25 years, planetary systems look different. They all look quite different. We've not found anything that looks quite like our own solar system yet. Here's just a couple of examples of the sorts of planetary systems that have been discovered. The top here is TRAPPIST-1. Again, compared to our own solar system. And you can see within Mars's orbit, TRAPPIST-1 has 7 planets. The green region here shows you what's known as the habitable zone or the Goldilocks zone. This is the zone at which liquid water can exist. So it's not too hot, not too cold, it's just right for liquid water to exist. So planets that are rocky and within the habitable zone are potential places where life could exist, at least life as we know it on Earth. Here's another example, the Kepler-62 system. This is quite a bit smaller than our solar system, except it's got 5 planets that are quite a bit bigger than the rocky planets in our own solar system. So there are many, many examples of a wide range of different types of solar systems and different types of planets. And so we want to understand how they form and try and inform us which one of these, are there any that might have the sorts of conditions needed to have life exist. So how will the James Webb Space Telescope do that? It's going to do that by using spectroscopy. So it has a near-infrared and a mid-infrared spectrograph detector on the telescope. This instrument, the way it works is it splits light up into its constituent colors. So you're all familiar with the fact that light can be split into the rainbow of colors. And you can do that with a prism, a glass block. And we can do that with light from stars too, right? So if we focus the light from stars through a prism, or actually we use slightly different things than that, but the principle is the same. You split the light out into the different colors. And when you do that, you can then search for signatures of different elements in the atmospheres of planets. So what we have is the light from the star passes through the light from the planet, so it passes through the atmosphere of the planet, and the atmosphere of the planet will absorb some of the light from the star. So here's an example. If there was lots of sodium in this particular atmosphere, then we would see absorption lines in the spectrum associated with sodium. Here's an example actually that was done with the Hubble Space Telescope, where methane was detected in the atmosphere of an extrasolar planet. So with Webb, it's set up to be able to search for signatures of different elements in the atmospheres of extrasolar planets. And ultimately, what you want to do is try and find the signature of an Earth-like planet. So what would an Earth-like planet look like? Well, there'd be significant amount of water vapor in the atmosphere, and methane, carbon dioxide, and ozone. And so in the near infrared and the mid-infrared, we can search for these signatures in the atmospheres of planets. And if we see something like this, we know we found an Earth-like planet. And that can be a good, potentially good place where there might be life elsewhere in the universe. Finally, one of the other cool instruments that's on the Webb Space Telescope is known as a coronagraph. This is essentially something that blocks the light from the central star, the bright central object, and allows you to see faint things surrounding it. So here's some examples that have been done in the past. This is a coronagraph on the Hubble Space Telescope. And in this little box here, it found a planet. And you can see over 2 years, you can see that the planet is moving in orbit around this central star. People have done this from the ground also with the Gemini telescope that's in Hawaii. And they found a planet, this one here, that's labeled with B, orbiting at a distance of around about the similar sort of orbit as Saturn's orbit around the sun, around its parent star. So with the James Webb Space Telescope, we will be able to scientists will be able to use the coronagraph to be able to pick out and directly image the light from planets around other stars. So Webb is going to be this absolutely fantastic telescope that can address a wide range of interesting science questions, from looking in the early universe, peering back to the first stars and the first galaxies, trying to understand how those galaxies have changed over time and have grown to form the grand, beautiful spirals and elliptical galaxies that we see in our local universe. And then how in those galaxies, stars form. And from those stars that form, how planetary systems are born. And then whether any of those planetary systems look like our own solar system and have an Earth-like planet that may harbor life. So these are the themes that are driving the Webb Space Telescope. But I think it's always important to remember that many of the greatest discoveries in science have been serendipitous. So there are many examples. One in astronomy, for instance, is the discovery of pulsars, which are rapidly rotating neutron stars by Jocelyn Bell Burnell in the 1960s, was completely unexpected and not what the telescope that she was using was designed for. But it opened a whole new world. And so there are many things we don't know what we're going to find. And it's going to be exciting being able to use the Webb telescope and be able to see what wonderful things it will do in the next few years. And so I'll stop now and take questions.
This is great, Ed. Thank you. I have a ton of questions for you that range from one from Matt Barrett over in Japan that I'll say is a little pedantic. I can say that because he's my friend. To some very detailed ones. So I've tried to put them in an order that's kind of going to go from some of the basics to some of the more complex science questions for you, if that's okay. The first was just thinking about the telescope and the way that they designed it. Is there a reason they didn't go for microwave instead and trying to look for really early material? Would that have been better for looking closer to the Big Bang than infrared?
No, if you go to a microwave, you would actually be sensitive to the cosmic microwave background. So microwave telescopes before have been put up, like Planck was the most recent one. That actually also, interestingly, was in orbit at the L2 point. And so microwave lets you look at the cosmic microwave background, which looks even earlier in the universe, but wouldn't give you a view of the first stars and first galaxies.
Okay. Someone else was asking about when they were doing the testing of the James Webb here on Earth, did they actually take any images out into space while they were testing it that are available?
No, so what they do, I mean, they did obviously extensive testing. They test the optical path, of course, and so they make sure that light is traveling through the telescope the way it should do. They test each of the individual optical elements, so they make sure that the mirrors are as perfect as they can be and as aligned as perfectly as they can be. And so there's obviously extensive testing that they go on to making sure that everything works. But they did not take any images out into space.
Now we just have to cross our fingers that it all goes the way that it logically should. But okay.
Yes, so Hubble, famously, Hubble had problems with its optical path. It was actually wasn't built perfectly. When they took the first image, it was blurry. And so the great thing about Hubble was it was serviceable. So they were able to go up with astronauts and 3 years later fix it to get the beautiful images that we see today. That's not going to be possible with Webb. So we have to trust in the engineers that they did the right testing, which I'm sure they have done.
If you want to learn more about that, everyone, you can check out the previous lecture by Dr. Christensen. Oh, we talked a lot about that. I'm still nervous until we see the images. I'm sure everybody is, but yes. Related to the different science themes, is there a priority of the projects for Webb? So is it going to start with looking at early galaxies and then go on to exoplanets, or how are they organizing the science planning? So the way that it's done, I think there is a core set of observations that are going to get done to start with. And then it actually goes to the scientists across the world. There was cycle 1 proposals were submitted and accepted. I guess it was earlier this year. I can't quite remember the timescale, where people from across the globe could propose what science they want to do with Webb. And they typically try and balance the different fields so that it's not all just staring at the earliest universe or staring at exoplanets. There's a real mix of trying to do everything. Got it. Okay. All right. This was a question Alec had after we were talking about the Lagrange points. He wanted to know if the telescope is going to be able to use parallax to determine the distance of stars, or if it's too difficult when they're that far away, but if being at the L2 Lagrange point might give it a wide enough orbit that it could use parallax.
So it's not designed to do that. And there's actually a telescope called Gaia, a European Space Agency telescope called Gaia, that was designed specifically for measuring the parallax of stars in our own galaxy, and has measured parallax of billions of stars in our galaxy, and gets as accurate distances to those as possible.
Matt's question was, can you technically consider exoplanets planets? Because you can't tell if they've actually cleared their orbits. So that's Matt's from Japan. So I had to throw it in. Technically, probably can't tell.
Yeah. We call them exoplanets. We're not calling them exodwarf planets. Not yet, anyway.
Will the sun shield of the Webb be able to withstand bombardment from micrometeors, or are they going to be a problem for it?
That's a good question. I don't know the answer to that. I'm sure they would have thought about that and designed it appropriately, but I don't know. I can't answer that.
Okay. All right. I think it came up in the last conversation as well with Mark, but I don't want to speak for him, so I'll have to check the video on that. Okay, then I'm going to check the chat for more questions, but Jeff had a lot of questions about star formation. So these are getting a little more specific science questions and not necessarily about Webb in particular. So I'm going to try to put them in an order that makes sense, but Jeff, I apologize if I get them out of order. Can we predict the masses of the initial star forming clumps that we're looking at early on? Is that something that's been done and what we think we should be seeing?
So we think we understand the conditions that are required for clumps to collapse. It's a thing called the Jeans mass, which is a condition for what's the maximum mass of a cloud at a given temperature that it can be before it collapses to become a star. Similarly, we also know what the distribution of initial masses of stars are. So there's a thing called the initial mass function, which tells us when you form a star, how many of them are low mass stars compared to how many of the high mass stars. And it turns out you form way, way more smaller stars that are something like half times the mass of our sun compared to the 20 or 30 times the mass of our sun big stars. So we know sort of what range of masses get formed, and we know what conditions are needed to form stars. So when we look at these molecular clouds, you can measure temperatures and densities and try and get a good estimate of what the conditions are there and what sort of star might form. Or stars, usually they form in groups.
Okay, he had a related question that I think you've answered now, but I don't know if there's a brief answer to this, but what determines whether you end up with a lot of smaller stars or just a few or one larger star in those processes?
It's the density and temperature within the cloud, essentially.
Got it. Okay. Let's see. Relatedly with star formation, how long does star formation rate vary with star forming cloud mass? I'm not sure if I wrote that right. Does that make sense? That may not make sense.
Star formation rate depends on how many stars are forming, depends on the conditions. And so there are things like, it's not just how massive the cloud is, depends how dense it is. And things like a nearby supernova can cause stars to form. So what can happen is that supernova will blow gas away from its surface. And if that collides with a nearby gas cloud, it can cause a shock front that can actually start to give overdensities and end up forming stars. So there are a whole bunch of different things that can cause star formation. Supermassive black holes, we think, can even cause star formation. So they can spit out jets into the galaxy. They can blow winds, and those things again can push material together and either, in some cases, start star formation going. In other cases, blow the material away and stop star formation. So there's a whole bunch of complex things that determine the rate at which stars form.
So related to that, there was a question about, I'm going to sort of modify it a little bit. The initial question was, will Webb be able to see the moment when stars gain enough mass to start nuclear fusion? But I guess relatedly, is that the kind of thing that we can actually spot at this distance? Or, I mean, is it's such a brief moment that that's happening in, right? So we'd have to pick it up sort of if we happen to see it.
When protostars, say ones in our own galaxy form, they're usually shrouded in dust, right? So you never actually, on the surface, you would never actually know that nuclear fusion actually started, right? Because it's buried right down in the very densest central part of the star. And it actually takes many thousands of years for that light to get out. So we won't necessarily see the moment where star formation where stars start doing nuclear fusion for the first time. The interesting thing about the first stars, something I didn't say, is that they are formed out of pristine material in the early universe. So the early universe was essentially almost entirely hydrogen with a little bit of helium, right? So 70-something% hydrogen, 20-something% helium. No carbon, oxygen, nitrogen, any of those heavy elements. And so this means that the first stars that formed were actually expected to be significantly more massive than the current stars that we see, probably 100 to 300 times the mass of the sun. They will be extremely short-lived because of that, and they will go supernovae very early on, after only a few million years. They will form black holes, and those black holes will go on to merge to form the supermassive black holes we think at the centers of galaxies. Now, the signature of that we want to see with Webb is this signature of what's called reionization. So this is when the light from those first stars hits this neutral hydrogen and helium gas and lights it up for the first time and ionizes it, strips the electrons off it. And signatures of that ionization or reionization what will give us the clues to what's going on in the very early universe. Was I going to say something else then? No, I lost my train of thought. I'll stop there.
That was good. That was there was going to be a question about reionization, so you got ahead of me. That's good. Related to that then, there was a question about how the presence of metals that were ejected from the first supernova, how will that have affected subsequent star formation?
Yeah, so that was actually what I was going to say, right? So the first stars, they will fuse from hydrogen all the way up to iron. So they will produce carbon, nitrogen, oxygen, silicon all the way up to iron. Then when they go supernova, they will not only push all that material out into space, they will also, in the supernova explosion, you also start to form heavier elements. So suddenly you've gone from a universe that's hydrogen and helium only to a universe that's starting to get carbon, nitrogen, oxygen, silicon, iron, other heavier elements. Then the second generation of stars that form will have those heavier elements in them. And those planetary systems that form around that second generation of stars will have those heavier elements. And so as you go to subsequent generations of stars, they get enriched and enriched by more and more by heavier elements as each subsequent generation creates more and more heavier elements.
Got it. Is a supermassive black hole necessary for galaxy formation, or does galaxy formation induce the formation of supermassive black holes?
Chicken or the egg, right? We don't know. So that's a question that a lot of people are trying to understand. There's for astronomy, is a really tight correlation between the mass of a black hole in a galaxy and properties of the galaxy, like the mass of the galaxy's bulge. And this tells us that the black hole and the galaxy know about each other. And this is actually surprising and interesting. So why is it surprising? Well, the black hole, even though it's millions to billions of times the mass of the sun, is typically only something like 0.1% of the mass of the entire galaxy, right? So it's actually a tiny fraction of the mass of the galaxy. And then on top of that, The black hole itself, supermassive black hole itself, is really small. These supermassive black holes are smaller than solar system sized, whereas the galaxies themselves are many thousands of light years. Right, so you have an object that's a small fraction of the mass of the galaxy, and a small size compared to the size of the galaxy. Yet the galaxy knows that it's there because its mass of the black hole and mass of the galaxy correlate beautifully. So there has to be some feedback process between the two. And we think that the way that black holes accrete material and irradiate the surrounding material acts as like a throttle for starting and stopping star formation in galaxies. And so the growth of a black hole and the growth of the galaxy appear to be tightly correlated, though we can't say which one came first.
Got it. A different angle now. Do you know, will the Webb be used for detailed tracking of comets and comet trajectories?
Yes, one thing I haven't talked about is actually the things within our own solar system. So it's planning that Webb should look at Mars and the other planets. It will look at asteroids. I believe it will look at comets too. I'm not sure whether it's going to track comets, but it certainly will look at known comets and study their properties.
That's great. I think I hit most of the questions that were in the chat. Oh, we got another one coming in. Let's see. Some comet water ice has a crystalline structure that's different from that of Earth's water ice. And there's recently been a publication claiming a superfluid, a fourth phase of water. And what are the implications for planet formation or origins of life?
Not quite sure how to answer that one. What I will say is that one of the ways that people think that the amount of water we have on Earth got here was from collisions of asteroids and potentially comets coming into our solar system, in the early solar system, and colliding with the Earth. So it can be that comets and asteroids that come from the outer solar system can actually bring water with them to planets. So that's sort of, I guess, a link between the two of them, I guess.
All right. We've had lots of thank yous in here. People really enjoyed your presentation and are grateful for you answering all of the questions as well. So thank you for that, Ed. I think Matt just said thank you in Japanese. So this was great. I'll let everybody know too that we have another lecture in this series coming up in January by another Wayne State faculty member, David Sanabro. That's going to be his cosmology talk called, I believe it's Doomed, Ignorant, and Insignificant, something, I don't remember the order of those, but he will be discussing an overview of cosmology and what we know about it and what we don't know about it at this point. So there's a link to that in the chat, so you should be able to find that. We'll also have a lecture coming up in February through the planetarium. That's part of our travel log series. It's a little bit different, less scientific. Our journeys with Jerry that we've been doing during the work from home period. Emeritus Professor Jerry Dunifer will be taking us to visit the Large Hadron Collider and LIGO. So he's taking us to the very, very big machines here on Earth and showing you how to get there, what's there, so you can take a tour of it yourself. So we don't have an event posted for that yet, but it will be on the planetarium's website once we are in the new semester. So keep your eyes out for that as well. And Jennifer, I think we're going to try to keep doing more of these events, and you certainly are.
Definitely like to. I've been doing monthly events since last spring. Usually try to make it the fourth Tuesday of the month, and obviously we change that schedule when needed. But the next one is January 25th, and I think I've still got it in my clips. So that's the link for Eventbrite. I don't harvest email addresses. If you would like to be on a mailing list for information like this, you can send me an email directly. And you also, when you're on Eventbrite, can choose to follow the poster. Not that I'm trying to get more followers, but it's a way to be informed of the events that we organize. So thank you very much. I really appreciate it. It was a great talk, and we're getting a lot of thank yous, as Megan said.
You're welcome. Pleasure.
Yes, thanks, Ed. This was great. And we will host, at the moment, we're not hosting live events at the planetarium yet, but hopefully once things cool down around Detroit, we will be hosting public events in our planetarium again. So again, stay tuned on our website and our Facebook page and at these events to find out about that.
Okay, thank you everyone for coming. And thank you so much, Ed. I really appreciate it. Goodbye. Good night, Megan.